Well, welcome back, guys. Oh, all right. As I sent an email concerning the days of exams, I said that I'll be here. Normally, if we were on campus, obviously we're taking an exam, but here we're going to continue the lectures. So on exam days, if there's any questions about the exam, if you're not taking it, now's a good time to ask. If not, I will continue with the chapters. And the advantage of doing this is that at the end of the semester, we're going to end up with maybe maybe three sessions that I call study days. Basically, getting ready for the final exam. I'll be here. You can come in with questions. It's like an open classroom. So anyway, any questions about today's exam? There is. Don't forget, there's an exam today. Okay. You
Yeah,
got you got to 11 p.m. and it's timed at 75 minutes.
yeah,
Yes.
I went ahead and just finished the exam. How
Okay.
long until the written portions are graded?
Okay. This weekend, I'm giving the exam to two sections, and I will have to grade my part, which I think is like three questions or short answers. So you should get everything up and running Sunday for sure. Okay, because I'm doing this one, my other one, and plus the other assignments that I.
For sure. Thank you.
Yeah, sure, no problem. Okay. All right. Any other questions, comments, concerns? You're ready to get into some real chemistry? Okay. All right. Well, I'm going to start chapter 4. Okay. Because now we're going to start talking about the models of what we think is happening with respect to atoms and how they're put together. Which is kind of fascinating because this model changes. And before we had no idea. We just thought, yeah, there they are. But now we learn how things are probably put together. Our data at the current time fits what we observe, okay, as far as the model that we have. Now, it can change tomorrow. Some new discovery, some new idea comes up, change tomorrow. But as it stands right now, this is our particular model. So the idea of the atom is not new at all. I mean, even way back in the days of the Greeks, they talked about matter and they used the term atoms. Now, Dalton is a scientist. So it was around there in the 1800s. He proposed his idea was that the element was made up of very tiny, indestructible particles that were called atoms. So that wasn't very new because atoms already were around, the term atoms. But it turns out that as we progress, they're not indestructible. In fact, we find out that the atoms are made up of subatomic particles. And we're going to talk about those subatomic particles. We're going to talk about specifically the proton, the electron, and the neutron. Okay. And this is not a topic for this course, but if you're interested, those guys are made up of even smaller material. Okay. But we're gonna stay with the three subatomic particles. Then Dalton proposed that all the elements were identical and had the same properties. Well, that sounded good until we start finding out things about like a diamond versus graphite. I may have mentioned this. A diamond is made up of nothing but carbon, pure diamond, 100% diamond, carbon. Well, graphite and even some lead pencils also have carbon. So you think, whoa, wait a minute. I got carbon and diamond, carbon and graphite, totally different properties, but the same atom. Okay. And it's a function of how these atoms are put together relative to each other, such that the diamond has a certain configuration of the carbon atoms that make something that's the hardest thing on Earth. And a different configuration of the carbon atoms makes something that's very slimy and we could be used as a lubricant. So that didn't turn out quite correct. he did postulate the following information. It said that atoms of different elements combine to form compounds. That is still true, in that we define a compound is a combination of, at the minimum, two different atoms or elements. So if we look at the reaction here, we have two diatomic models. They could be multiple things, but we could, let's just leave it as diatomic. So you can see their elements, they're diatomic, they're two spheres, same color. They combine to make something with a red and a gold combination. Could be anything. Okay, could be, as an example. So you can see we made a compound. So Dalton's idea is still true to this day. Also came up, excuse me, that with the idea that when atoms or the elements come together, they come together in whole numbers. They don't come together in half atoms or quarter, three-quarter atoms, anything of the sort. For example, H2O. That subscript tells us there are two whole atoms of hydrogen combined with oxygen to form the molecule of water, H2O. Okay, so they come together in whole numbers. And they can come together either with the same elements, but in different ratios. For example, CO, capital, both from capital, that is carbon monoxide. Okay, notice the prefix monoxide, meaning carbon and one oxygen, monoxide. And then you have CO2, which we're familiar name-wise, that is carbon dioxide. Okay. Now, when there's just one atom, it's assumed to be one. You don't have to put a subscript one. But obviously, anything more than one, you got to put a subscript. So we know. So there's two oxygens per carbon. Structurally, when you have one carbon, one oxygen, there really isn't a central atom. They're just bonded to each other. Okay. And that model on the left shows that. However, when we start dealing with more than one elements bonded to a atom, we have to show, and we always will tell you, who the central atom is. If you look at this, the carbon represented by the maroon color sphere is in the middle, and the oxygens are bonded around it. Okay, so you'll always be told who is the central atom. 99% of the time, it is written like carbon dioxide, where the first element written is normally the central atom, and everything else is bonded around it. Few exceptions, for example, H2O. H2O, oxygen is a central atom, and hydrogen is bonded. Those two hydrogens are bonded around it. By convention, people have written it like that, H2O, and therefore we keep it like that. So technically, it should be written OH2, but people don't recognize what it is in that direction. So there are a few exceptions. Let's see what else. Let me clear this. All right, now 1897. Now 1897, quite a while ago. Good old JJ. I like JJ. JJ Thomson was a scientist in England. He is credited with discovering the electron. He is also credited to making what we now know as a television, at least the old school television. You know, the big television, heavy one. Maybe your grandparents still have one. I had one not too long ago. Still good. What the heck? But what he did was he created some rays from this material, some particles. And these particles hit, and I'm going to show you a video here in a second. So I'm going to describe it first so you know what's going on. These particles would hit this material that it was a fluorescent material. Now, remember we're talking about energy. Nature doesn't like to be in an excited state. Nature always wants to get down to a stable state. These particles have energy in them, and they hit or collide on the surface, and they transfer the energy to the atoms on this surface material, and those atoms are excited to the next level, and they don't want to hang up there very long, so they drop back down. Well, when they drop back down, they have to emit energy, conservation energy. You're not making energy, you're not creating it, you're moving around. So if I take in 10 units of energy, I got to release 10 units of energy, and it releases it as light. The point being that these particles, he can visualize these particles as they hit the surface. And then he did some other things to show that these particles are charged particles. Okay, charged particles. Let me do this real quick. And I show you that the power of electrons in my background. Okay. All that is a battery, cable, copper cable, and a magnet. And you created a motor. Okay. Those crazy electrons, those same electrons that give you a bad hair day in the morning, we go poof, are traveling through that cable. And when you run an electron charge through a cable, it has with it a magnetic component. And so that's why that motor works. These were created by my physical therapy students at Carrington College. They put that together to demonstrate the power of the electron. Anyway, so with that in mind, let me show you this. Now, if you can see here, that colored screen, that's where you're sitting over here on this side watching your cartoons. Okay. So you can imagine that if you ever watch a movie of old television, you'll see the beam of the television screen going this. And what that is that electrical beam of scanning and created an image. Anyway, it creates this particle. The electrons, the material, these particles excite the surface as fluorescence. They absorb the energy and then they release it as light so they can see what's happening. As they put in a electrical plate there, okay, notice the current deflected. So you can deduce that that current must be charged, okay? It's a charged particle because every charged particle that's moving has with it a magnetic component. That's why that motor in my background is moving. Electrical currents, electrons are going through that copper wire, and then they create a magnetic component to it, which is attracted by the yellow magnet. And then inertia pushes that ring thing over and over. So it just continues over and over and over again, as far as the motor is concerned. Notice that when they put that charge, you had the negative side and the positive side, and they deflected that beam. So that tells you that beam is charged, okay? Okay, so as those particles are moving, they have a magnetic component with it. So here they put a magnet on there, the south side, which deflects that beam. And that's how the old-fashioned televisions work. If those in the back of the big old gigantic tube, there's 4 magnets that go on and off and on that direct that ray, so you can sit there and watch your cartoons. Okay. Anyway, here we go. Now, obviously, we're not going to have you responsible for this equation. This is way beyond Chem 130. But the point here was he was able to determine a value for that ratio of E over M. And once you know that, you have two variables now you can work with. And once you know that number on the right side of the equation, and then you can come back and determine what E is, guess what? You have M, which is the mass. And that's how they indirectly calculated the mass of an electron. So that's the value he got. It was a constant value. Later on, they were able to determine what the variable E lowercase c was, which then they could solve for M. And that gave you an idea of how small this crazy electron is. All right. Okay. So here's Thomson. So in 1900s, J.J. Thomson, okay, proposed a model for the atom based on his work. So he's credited with discovering the electron, and he proposed what's called a plum pudding model, where in the atom somewhere in there is a plus sign, plus material, and the electrons are all over the place, and hence they call it a plum pudding. We're going to learn with time that that's not the case, but for right now, in 1904, that was the model until, oh, let me back up, 1911. Okay, now keep this in mind. Look at the years here: 1911, getting into 1900. There's so much knowledge just came into port. This is just part of it, but this is the time of Einstein. Everybody knows about Einstein, but you got guys like Rutherford. You had guys like Planck. These were like something happened. Everything, knowledge of the atom just blew up, and we just got all this information. Here comes 1911. Ernest Rutherford, another British scientist. He is credited with discovering the nucleus. Okay, nucleus slash proton. Now, what he did was he was able to use particles, some different type particles. He also ran these particles on this material that had a fluorescent material on it. But what he did differently, he took the particles and he ran them through a sheet of gold foil. Okay. Now, with the plum pudding foil theory, what should be happening is that all these particles should shoot right through the gold foil with no problem. But what he discovered was there was deflection. Just like shooting pool, you're out there shooting pool, you get the ball and you want to hit the corner pocket. These particles were shooting off to the right, to the left. Some of them shot right back to the source, which kind of told them something else is going on. It has to be something in the nucleus that's pretty dense to cause this particle to ricochet off. So I'm going to show you the video. No, I was trying to stop it here, but here's the gold foil in the center, and the particles are being shot through. Most of them came through the front. You can see in the front the fluorescent material. But if you notice very carefully, some angled off. You'll see some fluorescence on the side, and so it kind of okay. Okay, so The model was this. They expected from Thomson's model on the left that most of the particles would go through. Okay. But you can see that they were ricocheting. Some of the particles were coming right back different angles. So that suggested that there's got to be, based on the mass of the particles they were shooting, there's got to be something in the atom that's pretty dense, that's not moving, and is causing these particles to ricochet off. Okay. And some, like I said, we're shooting straight back to the source. An analogy of that would be if you were to shoot a rifle, a bullet into a Kleenex, and that bullet came right back at you. And it's like, whoa, wait a minute here. So that proposed a whole new model then. So we got rid of the plumbing model and proposed that in the center of the atom is a very dense nucleus. Okay. And the electrons at this time are still somewhere around the atom. We're not quite sure. Not till later on that we get a more detailed model of how the electrons are put in there. So 1917, Rutherford is credited with discovering the proton/nucleus. JJ, good old JJ and Thomson, his contribution was the electron. And then about 20 some years later, a little bit less than 20, another British, I believe he was British, Chadwick, he is credited with discovering the neutron. So you see now we're getting to get a better picture of what the atom is made up of: electron, proton, and neutron. And then in the 60s and 70s, we start finding out that these guys are being made up of even smaller material. Now, the atom itself is mostly empty space, with the electrons somehow revolved around the nucleus, at least at this point in time, okay? So each atom has a very small and a very dense nucleus that contains the protons and the neutrons, okay? Now, to give you an idea of what kind of size we're talking about, if the nucleus was the size of, let's say, a small marble, then the atom, the whole atom, would be the size of a Cardinal Stadium. Another analogy would be if you were a hydrogen atom, for example, and let's say I was a hydrogen atom and I represent my nucleus, my electron would be approximately about 3/4 of a mile away. Okay, that's how much empty space is between there. And what's even extremely fascinating is that we got this electron that's 3/4 of a mile away, but yet it's still attracted to the nucleus. It's got a negative charge. The nucleus is a positive charge. And then there's some other force that's keeping it there. Because bear in mind, positive and negatives attract. Now, for some reason, that negative is out there. It's not collapsing. There's forces that you obviously don't have a clear understanding. You know, you ever heard of Halley's Comet? Halley's Comet? Anybody know how, when it comes around? Yeah, about 70 some years. It takes out of it goes around the sun every 70 some years. It comes back. You would think 70 some years, that guy is like way out there, but something pulls it back. Interesting. What is it that's pulling it back? Some say attraction. Well, yeah, but that's 70 some years of traveling is billions of miles away. Anyway, there's some forces we don't quite understand yet. Hoping to understand here for the next generation to put in your 2 cents. All right, so here we go. Subatomic particles. We got the electron, the proton, and neutron. Its symbol is a lowercase c superscript hyphen for negative because it has a negative charge. Okay. Its location is outside the nucleus, and we give it a -1 charge. I'll come back to the mass here in a second. The proton has a positive charge. Okay. And it exists in the center of the atom along with the neutron. The neutron has, guess what? Is 0 charge, right? 0 charge, hence the term, neutral, or neutrons. Now, the relative mass, these guys are tiny, extremely tiny. So it's hard to deal with extremely tiny numbers in these calculations. So what was done is give them relative weights or mass, atomic mass units. Now, that's like saying, okay, let's say I weigh 200 pounds. Well, let's say, because I'm not even near 200. Okay. Another person weighs 400 pounds. Okay. Now, my relative weight, his relative weight to me is 2, right? Because he's twice as big as me. My relative weight is 1. So that's what we're talking about, relative weights. We have given a relative mass of the proton and the neutron. We gave it a unit of 1. Okay. The electrons are so tiny, they're basically 0. If, for example, the proton weighed, we can use here 1836 pounds, the electron would be 1 pound. So relative speaking, 1,000 pounds versus 1 pound is nothing. So we essentially treat the mass of an electron as 0. Even though, keep in mind back your head that yes, it does have a mass. And what's even more fascinating is because that mass is so tiny that it behaves, and we're going to learn this, it behaves like light. It travels like light. It's so tiny. Okay, so with respect to scientific notation, what is atomic notation? Excuse me. This is how we write down the elements, okay? And there's a format. We have A, Z, and SY, okay? A represents what's called the mass number, okay? Z represents the atomic number, and SY is simply its symbol. Sometimes it's 1 letter capitalized, sometimes it's 2 letters, 1 capitalized, 1 lowercase, okay? Now, both these numbers are whole numbers. Keep that in mind, whole numbers. Now, excuse me, the mass number is the sum of the number of protons and the number of neutrons, okay, down at the bottom. The mass number is the sum of the protons and the sum of the neutrons, okay? Now, the atomic number equals the number of protons, which also equals the number of electrons. Now, if we look at the periodic table that we use, and we can take any of the elements, any of these elements here. We have the symbol. Let's take lithium, Li. Okay. The atomic number is 3. That tells you the number of protons and the number of electrons. So lithium has 3 protons, 3 electrons. Okay. Now, something else. The protons we just talked about have a positive charge. The electrons have a negative charge. So if I have 3 positives and 3 negatives, what is my net charge? If I gave you $3 and I took away $3, what's your net amount of money you got left?
Would it be 0?
Got it. Okay. 0. So all the elements up here have a net charge of 0. We're going to learn that depending who they are, they're either going to lose electrons or gain electrons. Now, somebody loses electrons that have negative charge, you become positive. Think of it in human terms. If you lose negativity attitude, right, you become more positive, right? What's the opposite? If you gain negativity, you become more negative person, right? The same thing here. We got electrons. Some of these guys are going to gain electrons, and that means they're going to have a net negative charge. Some of them are going to lose electrons, which means they're going to have a net positive charge. And you're going to be able to figure out who's going to lose. I already told you who always loses electrons, all the metals. All the metals here prefer to lose electrons. And when they lose an electron, they become positive charge. That is what you ingest. Sodium, the element sodium has 11 protons and 11 electrons. But when it reacts, it's going to lose 1 electron. Okay. In fact, everybody in this first column, 1A, will lose 1 electron, 1, and end up with a positive charge. The reason they're in the same column is because they have a similarity we're going to learn about with respect to electrons, and they react very similar. And that's why they're together in that same group. And that Roman numeral number there represents how many electrons are in what we call the outermost shell. But we'll have a lot more on that here in a bit. So, Tom, where am I at? The thing to where'd it go? To remember here is that the proton defines the electron. Excuse me. The proton defines the element. I was going back and forth and I was like, not thinking here. Now, on the modules I gave you, additional resources, there's one link called Build an Atom. And if you click on that link, it brings you to this. And if you get a chance, play with this thing because it's going to help you demonstrate how it gives you a better understanding of how the elements are put together. You have three little buckets here, labeled protons, neutrons, and electrons. Okay. Now, if you grab a proton and just bring it to the X, if I bring it anywhere near it, guess where it goes? To the center. Okay. And guess what? You made hydrogen. If I grab another proton, boom, goes to the center. Okay. It's not very stable right now. But guess what? Let me take out the stability. It made helium. Okay. If I grab a third one, I made lithium, and so forth and so forth. Now, if I get a neutron, I'm in beryllium right now. I grab a neutron, I put it in there. Guess what? I'm still in beryllium. Okay. If I grab an electron, I put it in there. Guess what? I'm still in beryllium, right? So what can you deduce from the three subatomic particles? That the protons define what that element is. I just made boron. Okay. Neutrons do not define that. Now, let me reset here. If I take one proton, I make a hydrogen. Hydrogen, its net charge right now is a +1 because it has no hydrogen, right? No electron. Electrons have a negative charge. When I grab an electron and I put it in there, it goes to the first dotted line. We're going to learn that these electrons actually exist in specific energy levels. So it fills the first electron. Look what happened to the charge. 0, because I got one positive and one negative. Okay. Now I can add a neutron. Now the other thing, look at my mass number is 1, because I have only one unit of mass, and that is the proton. The electron is atomic mass unit is 0. If I grab a neutron, it goes to the center, and I still have hydrogen, but I have a new mass number. Okay. And if I grab a second neutron, I have a new mass number. I haven't changed. I still have hydrogen, but I've added weight to the element. Okay. I am what I'm doing right now. By adding neutrons, I am making isotopes. So we're going to have all the elements have isotopes, and all that means is they have additional weight by adding neutrons. Okay? The neutrons. Now, we can lose neutrons and lose electrons all day, gain them or lose them all day, and we don't change what the element is. But the moment we change a proton, we change the element. Okay. All right, let me go back to the periodic table. So the mass number is a whole number. If we look at the periodic table again, and we look underneath the symbols, like sodium, here's sodium number 11. Underneath, you have a number, a decimal number, 22.99. That is what we call the atomic weight. Okay. It's a decimal number. It's not a whole number. Okay. It's a decimal number because it is an average of whole numbers. Now, these numbers, these atomic weights, we don't use in our calculations with respect to sig figs. Why? Because we will learn that 22.99 came from the average of whole numbers. And when you average whole numbers, you have an infinite number of sig figs. And therefore, we don't use the atomic weights to determine whether we have the correct number of sig figs in our calculations. We will be using them to do our calculations and use these in the periodic table because yes, you can go to the internet and find the different atomic weight, adds more digits, but then when you do your calculation and you input that number, Canvas won't recognize that number because it's not smart enough to know that. So all the calculations that deal with atomic weights deal with the atomic weights on this periodic table. So remember that, okay? Now, go back. So from the periodic table, at a glance, any of the 118 elements, you know two things. One, how many protons, and two, how many electrons it has. So element number 23, 23 protons, 23 electrons. And you know a third thing, its charge as an element is 0. They're all 0. All 118 of them are 0 because they have an equal number of protons and an equal number of electrons. Okay. So every element has the same number. Every atom of an element has the same number of protons. Excuse me. And like I said, the number of protons defines an element. Carbon is element number 6. It has 6 protons. Okay. And 6 electrons. It can pick up neutrons. It can pick up, we can have carbon 11, carbon 12, carbon 13, carbon 14. And I'm sure you've heard of carbon dating. Okay. That is looking at old material and determining their age based on carbon 14. Okay. It's still carbon. The only difference is that it has an additional number of neutrons. We'll get to that here in a bit. We did talk about the atomic mass units having approximately 1 for proton and neutron and 0 for the electron. Okay. So how do we calculate the mass numbers? Okay. Because we know that the mass number is the number of protons plus the number of neutrons. So what we do is we can rearrange that equation and say to determine how many neutrons you have, that will be equal to the mass number plus the number of protons. Okay. So what do? We go to the periodic table and let's look at carbon. Boy, we stick at sodium. This is highlighted here. So we take its atomic weight of 22.99 and round it up to the nearest whole number, so it becomes 23. Okay. 23 minus 11 gives you what? Starts with the letter T. What is 23 minus 11? 12. Okay. That means that sodium has 12 neutrons, 11 protons, 12 neutrons, which is equal to 23. Look at magnesium, next one over. How many neutrons does this magnesium have? Well, step 1, 24.31, rounded up to the nearest whole number, which is 24, and subtract 12. So magnesium, this magnesium has 12 protons, 12 electrons, 12 neutrons. You see that? Okay. Look at hydrogen, very first guy, hydrogen. Hydrogen has 1 proton. Take the 1.01, round it up to 1. 1 minus 1 is what? 0. How many neutrons does hydrogen have? This hydrogen, 0. Okay. Can it have more neutrons? Yes. And when they pick up neutrons, they become isotopes. Okay. Now, the reason we can do that is because these atomic numbers, they represent, when we round it up to the nearest whole number, they represent the most common isotope, in this case for sodium, because there's more sodium-23 in the environment than the other isotopes. And so when we, just like you grade, you have a percentage for your homework, a percentage for activities, a percentage for exams, okay? Each one brings a contribution to your overall grade. When we look at the percentage that exists in nature for all the isotopes of the element, obviously that element that is most common in the 90s, and we take their numbers, the whole numbers, multiply it by the percentage that they're in nature, it averages out to a number that's close to the most abundant isotope in there. I'll give some more examples to explain that. Because right now it looks like it's clear as mud, right? All right. So for example, they're asking you here to write the atomic notation for potassium. Well, let me do this first so we get into isotopes, because I see a lot of cases that are saying, I don't know what you're talking about. Okay, let's go back to hydrogen. Okay. Hydrogen had atomic weight of 1.01 from the periodic table. If we round that up to 1 and we subtract 1 minus 1, we have 0 as far as neutrons. But this is the most, and that's correct. This is it. Notice we got no neutrons here. We have a mass number of 1. Okay. A net charge is 0 because we got 1 positive and 1 negative. Now, the moment I put in a neutron, I still have hydrogen, okay? But my mass number went up to 2. So now I have hydrogen hyphen 2. The first one was hydrogen hyphen, just hydrogen, okay? If I add a third one, I get my mass number of 3. I've made another isotope. I still have a hydrogen. Let's do this, and maybe because we're more familiar with carbon, because you all know about carbon dating. Let's make carbon. So we need 6 protons here. So we're going to add 6 protons. Okay. And guess what? We made 6 protons, right? 6 protons represent carbon. All right. Now, what else do we know? We know that carbon 6 has 6 electrons, 6 protons, 6 electrons. So let's grab 6 electrons. So if I grab 6 electrons, if I move them toward the center of the nucleus, guess what happens? It slides to the dotted line. Okay. These dotted lines represent energy levels. And what's going to happen is if I do a second one, it's going to go to the first energy level. If I do a third one, you're going to be surprised. It goes to the next one, because the very first one, I can only put 2 electrons. And we're going to learn about that. So right now I got 3 electrons. Notice my charge is +3 because I got too many protons to balance it out. So now I have carbon, okay? Carbon 6, all right? Which is a net charge of 0 because I got 6 positives, 6 negatives. Now look at we just did a calculation. Carbon had a 12.01. We round that up to 12. 12 minus 6 is 6. So carbon has 6 neutrons. So that's 2, 3, 4, 5, and 6. Okay, that is carbon 12. That is the most abundant carbon. There's also carbon 11. If I take 1 neutron out, It's still carbon, but it's carbon 11 because it's missing one neutron. Okay. So I put carbon, I start off with carbon 11, and then the most common one is carbon 12. There's also such thing as carbon 13 and carbon 14, which is not very stable. It does break down. That's how we can use that to date things. Okay. So that is how isotopes work. Now, of these 11, 12, 13, and 14, carbon 12 is the most abundant. It's like 99%. And that's why when we average the atomic weights of 11, if you take the numbers 11, 12, 13, and 14, and just do an average of those, you're going to get a decimal number, right? Just that, because they're whole numbers. We have atomic mass units. All right, so we'll come back to that. Nope. Yeah. So what we do to write this notation, we say carbon hyphen 11, carbon hyphen 12, carbon hyphen 13, and the last one, carbon hyphen 14. Now and those are all the isotopes of carbon. All the elements have isotopes, okay? Some only have 2, maybe it's 3 or 4, they all vary, but all the elements have isotopes. And so when the next question pops up, it says to you, let me go to it. It says, how do you write the notation for carbon 40? All right, ask yourself the question, potassium 40. Is potassium the most common isotope? But to answer that question, you go to the periodic table, look for potassium, which is K. Take its atomic weight of 39.10, round it up, okay? And that is 39. So potassium 39 is the most common isotope here, which means that potassium 40 is not the most common isotope, okay? So to write that, we got to find the symbol, which is K. 40 is given to you. That's the atomic number, the mass number. 19, you got to find that from the periodic table. That's the number of protons. Now, potassium 39, if this was potassium 39, then we would write 39 on top, the most common isotope there. Now, how many neutrons are here? All you got to do is subtract 40 minus 19. So you don't have to calculate the 40 because it's given to you, hyphen 40. Nothing to look up. Okay, that is correct. 21 is the number of neutrons. That's 40 minus 19. If this was potassium 39, how many neutrons would that have? 20, right? 39 minus 19. Okay. Now remember, the notation is on the left side of the symbol, not on the right side. So it'll be superscript left, subscript left for the atomic number. Okay, not the other way around. The atomic notation for bromine 81. Let's check first. Is bromine 81 the most abundant? Well, we got to go to the periodic table. Okay, we look for bromine, which is Br, and it's sitting right here. Its atomic weight is 79.90. Round that up, that gives us 80. So the most abundant isotope is bromine 80. So now we're talking about bromine 81, which is an isotope of bromine. It's still bromine, but it's bromine 81. Okay. And we got to find its atomic number, which is 35. The number of neutrons is simply 81 minus 35, which is 46. So bromine 81 has 35 protons, 35 electrons, 46 neutrons. Okay. And it has a net charge of 0. This is the what we're talking about, except it's missing carbon 11. Now, carbon 11, carbon 12, carbon 13, carbon 14, they are all carbon. The only difference is the number of neutrons. They all have 6 protons. They all have 6 electrons. They differ in the number of neutrons, okay? And those are the isotopes. So carbon 12 has 6 neutrons, carbon 13 has 7, carbon 14 has 8. Carbon 11 would have 5 neutrons. Those are all the isotopes. We can, what they want you to do here is we got a table. You'll see this quite a bit in homework and exams and such. You get a table of the different isotopes. Everybody here is oxygen, right? But they differ because you got 16, oxygen 16, 17, and 18. So their mass number is given there for you, 16, 17, and 18. The number of protons and the number of electrons are the same. It's oxygen, number 8. Where they differ is the number of neutrons, okay? And the most common isotope would be oxygen 16. That's the most common one. You go to the periodic table, atomic weight of oxygen 16.00, whole number 16. That is the most common isotope. Okay. Notice, obviously, all of them have 8 protons. All of them have 8 electrons because they are oxygen. Where they differ is the number of neutrons. And so let me color this a little bit different. And so the sum of 8 plus 8 is 16. 8 plus 9, 17. 8 plus 10 is 18. Okay. And that is a mass number. Remember, the mass number is a whole number. The atomic weight is a decimal number. A little bit different. Okay, so here they're asking why is the atomic weight decimal numbers? It's simply here. There's carbon 11, carbon 12, carbon 13, carbon 14. Carbon 12 roughly about 98.89% in nature. Carbon 13, 11.11%. And so taking trace amounts of 11, trace amounts of 14, there's an actual percentage. But if you take those percentages and you multiply it by the number and average those numbers up and the contribution that they have in nature, you end up with an atomic weight for carbon of 12.01, okay? 12.01. And so this is what I mean that, these are whole numbers, okay? Because they come from the atomic mass units, the number of protons and number of neutrons. And even if you were to average those numbers out, you end up with a decimal number, okay? But you have to also take consideration the percentage that each number has. And that's why the atomic weight of carbon is 12.01 on your periodic table, okay? And that is why we can take the atomic weight on the periodic table, round it up to the nearest whole number, and that would tell you which is the most abundant isotope on the periodic table. And once you know that information, you can calculate the number of neutrons you have for the most abundant isotope. All right. Carbon 13. So the question here says, use the periodic table to determine the most abundant isotope. So you have lithium-6 and lithium-7. Well, we do grab the periodic table, got to find lithium. Okay, lithium is Li, lithium is number 3, which is right there. It has an atomic weight of 6.94. Round that number up to the nearest whole number, and that becomes 7. Therefore, the most abundant isotope for lithium would be lithium-7. Okay? Didn't have to memorize anything. We just used the periodic table. Now you got chlorine 35, chlorine 37. Do the same thing, go to periodic table. Thing is, you got to find chlorine. It's Cl right here, number 17. Okay, its atomic weight is 35.45. Round that up, that's 35. That means that the most abundant isotope is chlorine 35, which is that. Okay. All right, so a lot of the isotopes are radioactive and not very stable. So therefore, you will see in the periodic table their atomic weight in parentheses, and that's simply because we can't. They're not stable, and we really can't analyze them very well. So it's just somewhat of a big guess. Like number 96, curium, who's, by the way, is named after Madame Curie. Yeah, Madame Curie. Anyone by chance know where Madame Curie's from originally? Some people say France, and I will say no. He's originally from Poland. She's Polish. She did marry a Frenchman. But the reason she was in France is during the time period, women in Poland were not allowed to go to college, couldn't get a higher education. So she had to go to France, where France at the time was the mecca for all the scientific work that's happening in the world. And she was a chemist, and she ended up with two Nobel Prizes. Pretty cool to get one, but she ended up with two. And then even more so amazing that her kids also got the Nobel Prize. So smart family. All right. So what about chemical formulas? We're going to talk about those briefly. So they don't really tell us necessarily the bonding order and how things are put together. I would give you that with time and tell you what is the central atom. I kind of briefly touched on that. Okay, and how things are put together. We will learn how chemicals actually come together and what kind of geometry they have using the tools and the tables that we have. Okay. But we do know, as based on the laws we have about how atoms come together in whole numbers, that the subscript tells us how many of each atom we have. For example, H2O, water, says that there are 2 hydrogen atoms and 1 oxygen atom. If there's only 1, it's understood to be 1. You don't have to write the number 1 there. Okay, only if it's greater than 1. So unlike the bonding, it doesn't really tell us. We don't see that it's H bonded to H bonded to oxygen. That's not what's really happening. But you will always be told who the central atom is. Okay. So, but the subscript tells us how many atoms we have of each. And so we don't change that. Once we put them together, those subscripts are etched in stone. We leave them alone. So here we have a formula, general formula. It just tells us that we have 3 carbons, 6 hydrogens, and 3 oxygens. Doesn't tell us anything about how things are bonded together, what it is. Okay, it could be anything. But the point of this is to say that there is a total of 12 atoms here in this particular formula. We will learn with time what that thing is, but right now there's only 12 atoms. Now, why would we want to know this? Because what we need to do is to figure out the atomic weight of each atom and how many atoms we have each to sum everything to get what we call molar mass. Carbon has 12.01. There's 3 of them. Hydrogen has its atomic weight is 1.01. There's 6 of them. Okay. Oxygen has atomic mass of 16. There's 3 of them. Add those numbers up, and that is the atomic mass, the molar mass for that molecule. We're going to need to do that. But first, we have to identify how many of each we have. Occasionally, you get something like this where you have a parenthesis, and you might wonder, what the heck is that parenthesis? Well, I'm glad you asked. Okay. I'm going to direct you to the periodic table, which you're going to learn to hate, right? On the periodic table, on the left-hand corner, there's a table listed as most common, what are called polyatomic ions. Okay. These guys are treated as a unit. They are put together and they're not changed. So nitrogen, in this example, there's 4 hydrogens bonded to that nitrogen. And that even has its own name. It's called the ammonium. Here we have nitrogen bonded to 3 oxygens, and we call that a nitrate. Okay, so on and so forth. Here's one that we use quite a bit. OH, it is a unit. It is a packet. That's called a hydroxide. Whenever we need more than one of those packets, we put a parentheses around it. So going back to the problem, you would see the NH4, the ammonium in the parentheses, and there's a subscript on the other side of the parentheses. We only need that parentheses when we need more than one. So that's telling us we have 2 ammonium packets. Okay, then we have a carbon, then we have an oxygen, 3 of them. So there are 2 nitrogens within the parentheses and 8 hydrogens total within the parentheses because of that subscript 2. There's 1 carbon and 3 oxygens. We have a total of 14 atoms in that formula. That, by the way, is called ammonium carbonate. Okay. So you might say, oh, okay. How does that help me? Well, it will, because look, where'd it go? Where'd it go? Where'd it go? CO3. Look at that name, carbonate. NH4. Look at that name, ammonium. So therefore, NH4 parentheses subscript 2, CO3, its name is ammonium carbonate. We're almost done, guys. All right. Here's a couple, 3 more that we want to go through. Now, of course, you don't know what they are right now, but I'm going to tell you what they are. If you drink soda pop, you drink a lot of the first one, H3PO4, aka phosphoric acid. But that's not important right now. What you have there is 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay. If you eat a lot of Plums, this is what you're eating. The next one. Here's that parentheses, that hydroxide. Okay. There's 2 of them. So that means there's 1 calcium, and Ca, 2 oxygens, and 2 hydrogens, aka calcium hydroxide. And then the SO4, also it's in parentheses. That's another of those polyatomic ion units that are kept together. There's 3 of them. And so you have 3 sulfurs, 12 oxygens, and 2 aluminums. Okay, its name is aluminum sulfate. So we have a total of 8 atoms for the H3PO4, a total of 5 atoms for the calcium hydroxide, and a total of 17 atoms for the aluminum sulfate. Now, like I said, eventually, once we identify how many of each we have, each one of these atoms has an atomic weight. And therefore, we can look up the atomic weight for aluminum, multiply it by 2. Look up the atomic weight for sulfur. I'm talking about the aluminum sulfate right now. Multiply that by 3. Look up the atomic weight of oxygen, multiply by 12. Sum all that up, and that is the molar mass for that molecule. Okay. But and we will need that information when we start calculations. So you need to be able to identify how many of each atoms you have in that formula. Right? The law of definite composition, like we stated earlier, that these atoms come together in whole numbers and they're set. We don't change them. And we can do a calculation and determine the percentage. So for example, H2O or ordinary water has 11.2% hydrogen, and it has 88.8% oxygen. And that is true for wherever you find water. Water here on Earth, water out in space would have that percent composition of 11.2 hydrogen and 88.8% oxygen. We use that ability to find a percentage of each one to help us to come up with formulas when we make a new compound. We send it up for analysis, tell us how much carbon it has, what percentage, how much hydrogen, the percentage, sulfur, whatever other atoms we want. And then we can back calculate to figure out a formula along with some other information. All right. With that being said, congratulations. We're done. Chapter 4. All right. So, yeah.